at limits and limit properties, which was the focus of our inquiry activity yesterday. So we start by looking at the concept of patterns of a function versus actual values of the function. So let's say, for example, we're looking at the speedometer at right. It's slowly increasing in speed, and we can say that based on what we see happening, based on the pattern of the needle, that our speedometer is going to get closer and closer to 120 kilometers per hour, even if it never exactly reaches 120 kilometers per hour. If we look at the graph of 1 over x right here, we can see that as x goes to positive infinity, or even as x goes to negative infinity, we can see that the graph is getting closer and closer and closer to a y value of 0. Even if 1 over x will never equal 0 because it's never going to touch the x-axis, what we can say is that the limit of 1 over x as x approaches positive infinity is 0. Again, the idea here being that our function is never going to equal 0, but it has a tendency and a pattern to get closer and closer and closer to 0 as x goes to positive or negative infinity. So this brings up what we call the limit of a function. The limit describes what value a function approaches as x approaches a certain value a. So if we look at the graph at right here, we can see that as we get closer and closer and closer to this point x equals a, that our curve is going to trend towards a specific y value, what we call L. This is what we call the limit of our function as x approaches a. L is what we call that limit, what we approach as we get closer to x equals a. In terms of limit notation, the way that we describe a limit is we say lim x approaches a, f of x equals L. What this reads as is it says as x gets closer to a, f of x gets closer and closer to L. What it does not say is it does not say that as x gets closer to a, f of x equals L. As we'll see in the next slide and as we're already hinting at, the limit of a function does not actually have to equal the actual value of a function at a certain point. So an example from our last slide is that if a function v of t represents a car's velocity, then we would say the limit as t approaches some time value a of the velocity is 120 kilometers per hour. Or as t gets closer to a, the velocity gets closer to 120 kilometers per hour. In the case of function 1 over x, we would say that 1 over x approaches 0 as x approaches positive infinity. So on that last point, does the limit of a function have to actually equal function value at a point? So this does not have to be the case. The limit of a function as x gets closer to a does not have to be equal to, there should be a 2 in there, whoops, the actual function value f of a. In fact, the limit could exist, but the function could not at x equals a. That's a little bit weird to wrap our heads around, so let's look at an example with the graph at right. So if we look at x equals 2 right here on our graph, we can see there's an open hole right here, meaning that f of 2 does not exist. Yet we can see that as we trace out our graph right here, and we pay attention to what's happening to our graph, we can see that as x gets closer and closer to, we can see that f of x seems to approach a y value of 4. So what we would say is that the limit as x approaches 2 of our function is 4 because that's the tendency and pattern of our function to approach, but the function does not actually exist at x equals 2 since there's an open hole there. To go back to our example with the car could be approaching 120 kilometers per hour as t gets closer to a, but if the car comes screeching to a halt with brakes, say there's traffic at time t equals a, then we would say that the limit as t gets closer to a is 120 kilometers per hour, but the actual value of the velocity at t equals a would be 0 since we brake and screech to a halt. So, to capture this in a nutshell, the limit is more concerned with patterns and tendencies of a function than actual function value. So what we're going to be looking at in class tomorrow is discussing what is the tendency of a function as x gets closer to a certain value, and how is that distinguished from what is the function's actual value at that point. So now we move for some conditions for a limit to exist. If we pay attention to the last two slides, we notice that there are arrows approaching from the left and arrows approaching from the right at a specific x value. That is because there's no preferred direction for how we arrive at the x value. We can arrive from the left or from the right. This forms the basis for what we call left-sided limits and right-sided limits. The left-sided limit notation uses a negative superscript, since we tend to associate negative, like negative numbers, with left of 0, and positive with the right-sided limits. So we can see right here, looking at this graph, is that the left-sided limit, as x gets closer to 3 from the left, would be 2, since that's what our curve approaches, while the right-sided limit would be 3, since we approach a y value of 3 from the right. So this forms the basis for the condition that we need for the limit of a piecewise function to exist. Okay, we require that the limit as x approaches a from the left side is equal to the limit as x approaches a from the right side, what I call the stitching agreement. We have to be certain that we have a definitive number that we agree upon that our function approaches, so we require that the left-sided limit equals the right-sided limit. If we look at this graph right here, our limit does not exist here because the left-sided limit approaches a different y value, 2, than the right-sided limit, which approaches a y value of 3. Again, to reiterate the point on the last slide, notice that the left-sided limit exists and the right-sided limit exists even though our function is not defined at x equals 3 because we have open holes here. So that's just to reiterate the prior condition, or excuse me, the prior point on the last slide. So some properties of limits. Limit properties obey the same properties as real numbers, so we can add limits. Okay, so if the limit of f of x as x approaches x naught is L1, and the same thing for g of x is L2, then the sum of the two limits is going to be L1 plus L2. The subtraction of the two limits is going to be L1 minus L2. The multiplication of the two limits is going to be L1 times L2. And the division of the limits is going to be L1 divided by L2. Of course, coming with the caveat that in the last property, L2 cannot equal 0 since division by 0 is not permitted. So let's take a look at verifying the existence of limits. For the piecewise function defined at right, what is the limit as x approaches 1, f of x, where f of x is equal to x squared for x less than or equal to 1, and 6 minus x for x greater than 1. So help organize what's happening, even though we should be familiar with piecewise functions at this point. What I like to do is I like to draw a number line. That helps me out a little bit, where I say for x, to the left of x equals 1, we have x squared, and then to the right we have 6 minus x. I use this bracket pointing towards the left to indicate that at x equals 1, my function is x squared. Hence the bracket points to the left. So what we do here is we apply our left-sided limit, okay, which is going to be the limit as x approaches 1 towards the left of x squared, since x squared is our left-sided function, and we get 1 squared equals 1. Now we apply the same thing to the right side. Oops, this is a typo. There should be a plus right here since it's the right side limit. The limit as x approaches 1 from the right side of 6 minus x is going to be 6 minus 1 equals 5. So as we can see, since the two limits from the left and the limit from the right are not the same, we say that the limit as x approaches 1 does not exist. We say D and E for short, since the two limits from the left and right are not equal. And we can confirm this by looking at the graph of f of x. We can see right here that this is what f of x looks like. It's a parabola to the left of x equals 1. And then we can see 6 minus x approaches a different y value as we approach from the right side. Lastly, evaluating limits algebraically. There are many methods for evaluating limits, but the primary method that we're going to look at today, to keep things simple, not throw too much at us, is by what we call direct substitution, meaning you just substitute in the x value to the function. So, for example, if I'm looking at the limit as x approaches pi over 4 of cosine of x, we just directly plug in cosine of pi over 4 to get rad 2 over 2. This is for a non-piecewise function here. So this is not the only method for evaluating limits, but again, we're going to keep things simple, and we'll keep the methods for evaluating limits to a separate lesson, 1.2. And this is the lesson for limit properties.